All right. So yeah, as Lynn mentioned on the slide today, I'm going to talk about how to design an operating system without using hardware protection, hardware support through the use of safe languages. But I'm also going to cover how typical conventional OSs work with hardware support. So hopefully this will tie in a little bit to your exploration in Rust and labs 4 and 5. So first off, what is a safe language OS? Right, so that's a system that relies on using language safety features to protect sensitive data or sensitive functionality from unprivileged entities like user applications, and also to ensure isolation between tasks or processes, depending on what you call them. They're almost always written in a safe language. They kind of need to be. And as such, they can forego the usage of hardware protection, like privilege levels. They rely on the compiler to perform checks about their behavior, like the actual OS code itself is checked by the compiler to make sure that all of these guarantees are upheld. I'll give examples of this later. And this often results in less overhead, right? At runtime, you can move a lot of the checks. At runtime, you're doing fewer checks, so you can move them to compile time. So you have the potential for higher efficiency. So a brief outline of the talk. First, I'm going to give a background on how conventional OSs ensure isolation. Okay, I'm not sure what that chat is. I'm going to talk about how conventional OSs ensure isolation. I'm going to talk about what hardware protection actually is. Then I'll talk about some safe language OS principles, how they work, and give you a general idea of the technologies used and the requirements therein. And then I'll talk about how we can go beyond language safety with more recent research developments in the space of safe language systems. All right. So in conventional systems, like Linux or Windows, they typically use hardware protection. And there are two dimensions of protection. Both of these are spatial, right? So the first is privilege levels, which is known as the ring model. This is basically saying if you're in a certain ring, at a certain level of privilege, you can only execute these instructions, right? And this is enforced by the processor. And then the other dimension is address spaces, which is sometimes referred to as virtual memory. They're basically the same thing. This effectively says there's a restriction on which addresses you're allowed to access. And this is enforced by the memory management unit. So privilege modes are typically depicted using rings, where the innermost ring, in this case ring 0, is the most privileged. And then ring 3 is the least privileged. So typically ring 3 is referred to as user space mode. Ring 0 is referred to as kernel space mode. You guys are probably familiar with this. So most privilege instructions are forbidden in ring 3. And depending on the architecture, rings 2 and rings 1 also may forbid some instructions. For example, you cannot change page tables. You can't access special system configuration registers or change system descriptor tables, which basically affect how the privilege modes work, unless you're in ring 0. So that makes sense. You also can't modify whether or not interrupts are enabled, to give another example. So the method of enforcement here is a CPU exception occurs if a higher ring, for example, ring 3, attempts to change one of the page table registers or something. So that will cause something like a general protection fault, perhaps a page fault. It depends exactly what the illegal instruction is trying to do. So in real life, typically we only use 2 of those rings. Ring 0 has the kernel and ring 3 has all of the applications. So there are some more recent developments, I should say recent, meaning within the last decade or so, that actually give even lower level rings, more inner rings, like ring -1 and ring -2 for hypervisor and system management mode. We don't really need to go into those, but they do exist. I just wanted to throw that out there. And that's x86 terminology. On ARM, they use PL, privilege levels 0 through 2, which is simpler, right? PL0 is the hypervisor, PL1 is the standard kernel, and then PL2 is user applications. So this model basically is how you ensure protection from untrusted entities executing instructions that are sensitive or could mess up the system configuration. So now moving on to the second dimension. Oh, before we move on, are there any questions on privilege modes? Any questions at all? Okay. Feel free to stop me, by the way, anytime if you have questions. So second dimension is address spaces. So first off, you guys are probably familiar with the concept of virtual memory, but you may not really understand why it's necessary or why we actually, why it's desirable, right? So first I'll back up a little bit. In terms of actual memory, real memory on the system, we call that physical memory, and it's addressed from 0 to whatever the maximum value of the addressability is, right? So 32 bits, 4 gigs, 64 bits, much larger. So this is basically saying there's a single set of addresses for the entire system, physical addresses at least. However, not all of those addresses actually exist, and this leads to a lot of holes in the physical memory space. Right. So here's an example on the right side of a sample x86 machine. In low memory, at lower addresses, maybe under 1 megabyte, you have BIOS areas, things to help the system boot up. You may have a very rudimentary VGA display that you see when you first turn on the machine. That's usually mapped in at hex A0000. And then you'll have bits and bobs, random regions of free memory all over the address space. And of course, that's liable to change based on how much DRAM you've plugged into your motherboard. Right. And then there will be a lot of random devices, such as memory mapped I/O devices, mapped in at arbitrary points. You don't know ahead of time, like your graphics card or other devices, peripherals through PCI, things like that. Right. All of these are accessible through the physical memory space. So because you have these holes, and because there's only one instance of this, it's really not a good idea to let untrusted user code access this. First, all processes would have to agree on who has access to which addresses. For example, if you only had RAM from hex 10,000 to hex 100,000 or something, when you're building the executable for your user program, you'd have to say, I'm going to use hex 20,000 to 30,000, and nobody else can use that. That's obviously completely impractical, right? Because it forces all of the user programs and the developers to have knowledge of the actual hardware on which they're going to run. So that's kind of the real reason, in addition to protection, that we use virtual memory instead. Right? So a virtual set of addresses is the solution to avoid allowing and forcing user space programs to access physical memory directly. And this requires the system to create a mapping between the virtual address and the real physical address before you can actually use that virtual address. And this is yet another layer of indirection that offers protection. In this case, the processor doesn't really do the checking, but you can think of the MMU as part of the processor. The MMU is the one doing this checking. It's the entity responsible for translating virtual to physical addresses. And this does add some overhead, but we typically reduce this by using translation classes, commonly referred to as the TLB, the translation look aside buffer. All right. So in order to actually set up this mapping that we encode in the MMU, the OS, more specifically the kernel, is responsible for setting up tables to define how a virtual address should be translated to a physical one. And this is commonly known as page tables, which you've probably heard of. All right. So this is the more modern scheme, again, in the last 2 decades, not particularly modern, that replaced the very archaic scheme based on segments of memory. All right, so I won't talk about that, but you can read about segmentation if you want. So just to give a concrete example of something, an actual virtual memory space, typically there's one virtual address space per process, right? So on Linux, for example, you'll typically see the text section, which is the program's executable code mapped at starting at this address, hex 400,000. And then, you'll have, depending on the size of all these other parts of your program executable, you'll have your read-only data, your writable data, and then space for libraries, which are typically shared across the system, across all of the address spaces, like libc or something. And then space for your heap, and space for all of the stacks for each thread in your process. Right? So what this allows you to do is have many different processes, and they all see their own view of system memory, right? They each have their own dedicated address space. They can only see those virtual addresses. They actually don't have any idea that there's a separate physical address space beneath, that actually accesses things in hardware. So what this means is that the process thinks that it has exclusive access to all of the system's memory. So for example, you could have two different processes and they both can reference hex 400,000, but get actual different contents in memory, right? Because they may point to different physical addresses. And the way that looks is something like this, right? You have this mapping from each one of these virtual memory spaces to the physical memory space, right? So this is an example of mapping each one of these to free DRAM. And then of course, for libraries, if those are shared, that would actually map to the same underlying physical memory address. Okay, any questions on this part?
I've got one.
Yeah, go ahead.
When I first learned about virtual memory in CS 323, it was, at least my impression at the time was that it was in order to consider like disk memory as if it was RAM. Is that sort of an extension of this? Like, is this really the primary reason and using disk as RAM is secondary or like an extension?
Yeah, so I would consider that to be a side benefit. I wouldn't say it's the primary purpose of virtual memory. It's a significant benefit, right? So the general concept that you're describing is memory overcommit, right? The process can assume that it has virtually unlimited memory, right? 32 bits or 64 bits. It has access to all of that memory, even if you don't actually have that much physical RAM on your system, right? So that's a major benefit. But the real purpose and kind of why I'm trying to illustrate this this point is to provide protection and to kind of offer a layer of abstraction so the user space doesn't have to know about the intimate details of the underlying physical memory map. But that's certainly a benefit, yes.
Thanks.
Mm-hmm. All right, great question. Any other questions on this part? Okay. So I'm going to move on to the pros and cons of hardware protection, right? So I just described the two dimensions of hardware protection. We had the privilege levels, protection modes, and we had the address spaces, right? So obviously there are benefits to this, otherwise people wouldn't use it. It's a very well understood and somewhat simple machine model, right? Your code, your program, or your kernel runs in a privilege mode and in an address space. So it's kind of easy to understand conceptually. And then in order to transition between these modes or address spaces, there are a series of special instructions called something like call gates. So that would be like a system call if you want to transfer a transition between ring 3 to ring 0. What this does is it allows basically any language to be used, even unsafe ones, because it relieves software from the burden of ensuring isolation, right? So hardware basically, us as system software designers would basically say, if we set up these tables right, hardware will ensure that isolation is there, no matter what language we use. But it doesn't come for free. When you're setting up these system tables and the interfaces for example, for system calls, you have to ensure that there aren't any unintended ways to switch between those modes or address spaces. Right? It can actually be quite complicated to set up these descriptor tables. For example, on x86, you have GDTs, task state segments, IDTs, all of these different things that if you misplace one bit, you could end up introducing a security flaw and allowing something like a rootkit to be executed from ring 3. Another big problem is that hardware is closed source, so we can't easily verify it on our own. We just have to trust that Intel, AMD, Samsung, whoever, they're ensuring that their verification is right and the hardware does what it claims to do. If you don't believe me, you can just look at the extensive amount of speculative execution attacks that have come to light in the past 5 years, namely Spectre and Meltdown, which is basically, I don't really have a lot of time to go into it, but basically processors were doing speculative execution, accessing memory for instructions that were going to run in the future. And then because they weren't clearing that access memory from caches, you were still able to read it. So for example, if a program if a CPU looked ahead and it accessed some kernel code to access kernel private memory, user space could end up reading it. So that's a big problem. We can't verify that doesn't happen. There's also pretty significant overhead when you're switching between these modes. For example, consider the overhead of a function call, which is from one ring to the same ring in the same address space, or versus a system call, which is from one ring to a different ring in the same address space, or hypercalls, which is from one ring to another, like a hypervisor or something, an underlying virtual machine monitor. Right? Each one of these has successively more overhead than the last. Right? Another thing is that it forces the design of the OS to follow the structure of the underlying hardware. And I'll give some examples of this. All right. So in a standard system, you may expect a structure like this. Right? On the x-axis, the horizontal plane, we have different address spaces. On the vertical plane, the y-axis, we have different privilege levels, right? So we have each process, and the kernel also is in its own address space, and all these processes are in, maybe ring 3, whereas the kernel is in ring 0, right? So you need to have an OS structure that mimics this, excuse me, because there's no other way to use hardware protection unless you, suit your kernel to its structure. So in practice, how does a real system like Linux, for example, use these different user space and kernel space address spaces and privilege modes, right? So before the recent developments of these speculative execution attacks, we had a relatively simple model, right? It was called a combined address space, or sometimes a merged address space, right? In which, if you had a 32-bit system, let's just use that for simplicity, from the 0th address to the 3rd gigabit address, that would be reserved for user space virtual memory. And then the final gigabyte from 3 to 4 would be used to map in the kernel's address space, right? So you had this combined address space. And what that meant is when you did a system call, basically when you switched from ring 3 to ring 0, you didn't have to change address spaces because the kernel, its code and data was already mapped into this current address space. So that made it really fast to do a system call. And similarly, when you did a context switch, specifically from one thread to a thread in a different process, a different address space, right? All you had to do was switch address spaces for this top part, just the user space virtual memory, right? The kernel virtual address space would stay the same because there's just one per system. Right? So this is pretty simple. But now that with the onset of these speculative execution attacks, kernel developers, specifically in Linux, have been forced to use separate address spaces now. And this is referred to as KPI, or kernel page table isolation. So just like we had before, we have the user space virtual memory and the kernel virtual memory. Now, when we execute a system call, we actually need to switch to a special kernel mode page tables, right? And this is an address space where most of the kernel is unmapped, right? Which we see down here. And the reason for that is we don't want, through a speculative execution attack, a rogue user space program to be able to access this kernel memory through speculative execution. So if we unmap it, it can't possibly access it, right? But you pay a cost, right? So then when you're returning from the system call back to user mode, you have to switch back to that original kernel page table, which includes all of the kernel code, right? So that's a little bit of a tedious, a little bit of extra overhead is added there, right? Okay, so this brings me to, I think, an overview of the two main types of OS designs, right? You guys are probably familiar with monolithic OS systems, right? Things like anything based on Unix, Linux, Windows, Mac OS, right? You have one large kernel, everything is in it, all drivers, file systems, all that good stuff. And then in the user space, you have, user space stuff, applications. Microkernels are I wouldn't say a new, but they're a different design where you basically try to have everything moved up into user space for fault tolerance reasons. If something crashes, it doesn't kill the whole machine. And you keep the kernel itself as small as possible. Some examples of this are things like Minix, any L3 or L4 based systems like SEL4, QNX, and even GNU has one called GNU Herd. So in a monolithic OS, right, which you guys, again, are probably really familiar with, so I'll breeze through it. This is kind of the more efficient design. All kernel code exists and it runs in a single kernel address space. So communicating with one kernel entity to another is very fast, just function calls, right? But it's less resilient, it's less fault tolerant. There's no separation between kernel entities. So if, for example, a rogue, malicious, or an errant driver has a bug, that can crash the entire system, right? All of the rest of the kernel components will be affected. right? So in this case, an application has to use system calls to ask the kernel to perform privileged operations, like accessing devices, for example, as opposed to just a function call or something else in a different structure. Now, in microkernel systems, they strive to move all of this kernel functionality into separate processes, right? And these are typically called system servers. So this leaves the kernel itself to be quite small. That's why it's called a microkernel. This offers more resiliency, better fault tolerance. So because each one of these kernel entities up here, right, executes in its own user process, it's more easy to recover from a buggy subsystem or a driver. So if one of these drivers crashed, that's no big deal. You can just restart that process. The whole kernel didn't crash. But you pay a little bit of extra overhead costs because instead of just communicating with function calls across kernel entities, you have to use IPC to go across each one of these, right? Inter-process communication. Sorry, my dog is going crazy. Hey, relax. Right, so this IPC is expensive because every time you do it, you have to do a context switch, you have to go down into the kernel so it can copy the data for you, things like that. There's overhead. All right. But because of the reliability, this is more popular in embedded systems and other computing domains where you need that reliability. Right? There are a wide variety of other designs that also use hardware protection, things like a multi-kernel where you have sort of one kernel instance per hardware core, and even other heterogeneous kernels like K2, which was from Lin's group actually, that explores different types of kernels for different cores of different power levels, right? So a weak core versus a strong core, right? So the point is that all of these use hardware protection, and the structure of each is kind of dictated by the underlying hardware. Right? Okay, before we move on, are there any questions on conventional OSs, hardware protection, anything like that?
Yes, another question.
Yeah.
So when you were talking about like Spectre and Meltdown, like the speculative execution attacks, you said one reason that it's bad is because we can't like verify the hardware. So like we don't actually know that we're exposed to that vulnerability. One thing I thought when you said that was that, well, if you can't know it's there, then you also can't patch it, just in principle because it's hardware. But then you were saying that Linux made a change in the kernel space memory in order to prevent those speculative execution attacks. How is it possible that you can use software to fix a hardware issue like that?
Yeah, so that's a great question. You can't always, right? In this case, the vulnerability was well studied, well researched, and then specific hardware manufacturers like Intel and AMD determined on their own which processors were affected, right? And then for those processors, they determined, here's a way that you could avoid this exploit, right? So the exploit in that particular case centered around accessing memory from an unprivileged entity that was privileged, right? So accessing kernel memory from user space. So the folks behind this exploit, behind the security team that discovered it said, if you don't map that memory in when user space is running, then there's no way that you can access it, right? And that's still true, right? So hardware cannot access memory that isn't unmapped, or what I should say is a user space program running on hardware cannot access memory that's not currently mapped, right? So you're right to say that you can't always patch every single hardware flaw in software, right? In this case, there was a solution. It's definitely not an ideal solution, right? There's a significant performance penalty, right? For varying workloads, I've heard it range from 5% all the way up to 30, even 40%. But yeah, in this case, this was just one that they could fix, right? And it's not even really a fix; it's just a workaround, right? If you read the mailing lists, the conversation from folks in the Linux kernel community, you'll see that they are not happy about the solution, right? This is a temporary patch with the hope that future processors will fix their speculative execution behavior to forbid this kind of thing.
Got it, thanks.
Yeah, great question. Okay, any other questions about hardware protection? Okay. So, right, that's how conventional systems have done it for all of time, and also in the modern age, these are still used. There is another category of operating systems that kind of forgo this, right? And we call them safe language operating systems, as I mentioned in the intro. So I'm going to talk about how they actually work, right? It seems kind of mysterious and ethereal. Oh, you know, Safe Language just handles it for us. But I'll give examples of how that works and why it's sufficient to forego hardware protection. So there are a few key concepts that I want to cover first, right? As I said, there is not a need for hardware protection, because the language and the compiler already have that covered. And I'll show you why. What this means is that everything can typically run in the same address space and privilege level. This is sometimes called an SAS SPL system, SPL single privilege level, meaning everything is in ring 0, and single address space, meaning that you're not switching between multiple process address spaces, right? It doesn't necessarily mean that you only use physical addresses, though some systems do. You could just have a single virtual address space, and that maps to physical addresses. Right? So this results in an efficiency bonus, right? There's no need to switch between privilege modes or address spaces, which does constitute overhead. And you also have a simpler programming model. It's very similar to writing a regular user space program. You just worry about everything in this one program, and that's kind of the whole system. There's no complexity of writing, you know, this is a server, this is a server, this is a server and process, and they all communicate with IPC, like in the microkernel case. So to compare a conventional OS versus a single address space, a single privilege level Safe Language OS, right? The structure would look something more like this, right? Like I said, everything runs in ring 0 down here. And each one of these red boxes represents an address space. So there's only one. So everything runs in the same address space, as opposed to monolithic systems where the kernel is in its own address space and applications are too, or microkernel systems where every little entity is in its own address space. So there are some fundamental mechanisms that enable those key concepts that I just discussed. So the key idea really here is that if a language can provide type safety and memory safety, and you can enforce it in the compiler, then you can prevent unintended behavior, right? And that's really what isolation and protection is about. It's about preventing unintended behavior, right? So what are some common concepts here? I tried to break it down into 3 core concepts. You know, this is my take on it, but you know, there's obviously going to be other opinions out there. This is how I categorize it. 1, you need to be able to ensure naming visibility. And that's a fancy way of saying that one piece of code can't access private data, things that are, you know, internal to another piece of code, like private field structures, private types, private functions, things like that. You also need to provide the ability to have capability-like objects, which is just to say that if you can acquire a certain object, you can only then can you invoke methods on that object or access its data, right? And then finally, you need to be able to have a set of operations that are forbidden. You know, for example, things that are unsafe, right? And you need to be able to forbid those at compile time for certain pieces of the system. For example, generally, user space applications shouldn't, or user applications shouldn't be allowed to execute unsafe operations, right? So examples of that are things like arbitrarily reinterpreting a particular type via arbitrary casting, or dereferencing random pointers, right? That's never going to be safe. Right? So the key point here is if we don't have unsafe code in an application, for example, there's no way for that application to bypass the above safety rules. Right? So I'll give some concrete examples of each one of these concepts. Right? But first, let me talk about type safety in an informal manner, right? So you've probably heard a lot about how Rust is type safe, and it can also offer memory safety. So what is type safety? Basically, in one sentence, it's when a language's type checking features can prevent undefined behavior. And I know that's really vague, but that's kind of the best way to describe it, right? So you can also think about what are you safe from, right? You know, if you're wearing a parachute, you're safe from smashing into the ground at high speeds. If you have a type safe language, you're safe from undefined behavior due to type errors, like type mismatch or something, right? What this really means in much plainer English is that you can't simply treat one type as a different incompatible type, right? So you can't do anything illegal, right? You can't do anything beyond what is sanctioned by a given type, what is supported by that particular type, right? So for example, you can't execute an operation meant for strings on an integer type. Right? So you can't do something like, you know, concat or run uppercase or lowercase operations on an integer, right? That just doesn't make sense. So that's an example of what type safety is. So as such, type-safe code can only access memory that it's been authorized to access through that particular type, right? So I'll give some language examples. Obviously, C and C++ are not type-safe, right? Python is type-safe, right? And the type safety is checked at runtime. Rust is also type-safe, and the type safety is checked at compile time, right? So here's some very simple Rust code. I have sum is an integer, it's a 32-bit signed integer. Hello is a string, and then if I try to multiply hello times sum, I'm going to get a type error, right? That just doesn't make sense. That would be undefined behavior. Any questions?
Yes.
Okay, go ahead.
Sorry, I've got too many questions.
That's fine.
What about
fine.
like in C, there exists something called union, where you specifically want to interpret the bits that the data is being stored in as multiple types. Is there any equivalent of that in Safe Language, or would you have to have like multiple copies of the bits that are interpreted separately?
It's a hard problem to solve because unions in general are unsafe, right? Even in C, they're unsafe, right? But C offloads the safety onto you, the programmer, right? So no, in general, there aren't unions. In Rust, there are things like, enums that have complex variants and things like that. But if you want to support, interacting from Rust to C, and the C code uses a union and you need to access that in Rust, you have to use unsafe code. Yeah. But in general, you can get around unions. They're not, I don't think they're a core language feature that are required. Okay, so the next step is, what is memory safety, right? So once you have type safety, you can also potentially ensure memory safety. So what are the requirements for that, right? So a language provides memory safety when its types can prevent invalid memory accesses, right? So what this means, again, in plainer English, is that all pointers will always point to valid memory. Now, what is valid memory, right? Again, this is up for debate, but the general interpretation of valid memory is it's currently allocated, it's of the correct type, meaning that you're accessing it through typed functions that expect this memory to be of a certain type, right? That's what I mean by correct. Expected type is another way to say it. And it's at the proper or expected size and alignment. So if you have memory safety, it can go a long way to preventing common errors. Two classes of errors are temporal and spatial, right? So temporal errors, things change over time. The state of the valid memory may change. And if you don't have memory safety, you could have things like uninitialized variables. You could have dangling pointers where you're potentially, you have a use after free case, or data races where you're interleaving writes and reads at the same memory location incorrectly, right? You can also have spatial problems like out of bounds accesses, which I think we're all familiar with, buffer overflow, underread, whatever. So back to the language examples, C and C++, similarly, not memory safe. Java is memory safe. It's checked at runtime, right? Everything is allocated and managed behind the scenes with garbage collection. And Rust similarly is memory safe, assuming that you use safe code. And it's checked at compile time generally. Most of the things can be checked at compile time, not everything. So here's an example of something in Rust that is memory safe, but it has to be checked at runtime. And that's an out of bounds error just because you don't know how large this array may be, right? In this example, maybe you could elide that check, but you don't always know, right? So this is, some bounds check. You could do something like this in C, and it would be potentially fine. Depends on your underlying memory map. Right. Any questions on memory safety? I know it's a complex concept, but hopefully more examples down the line will help you understand.
Why does that have to be checked at runtime? Because you're defining what ARR is at compile time. Like, only if it was like the user puts in like some unknown number of items and that gets put into ARR, would you not know if the 10th?
That's a good question. That's what I was hinting at when I said in this specific case, it's likely that the compiler with the proper optimization arguments could elide that bounds check, omit that bounds check, right? But it's not guaranteed, right? In general, this indexing operation, when you're accessing a slice, right, an array in Rust, it will have a bounds check here, and then it will panic if it's out of bounds. Right? So in general, it's not elided. That's up to the compiler, right? That's up to LLVM's optimization passes to remove that bounds check if it knows that it can do so.
Got it. Thanks.
Right. Yeah. So in this case, it wouldn't actually be able to remove the bounds check. It would just perhaps change it into an immediate jump to a panic, right? So maybe there would be one less condition, but it's not removing the bounds check. It's just immediately knowing that it will result in a bounds check failure. Okay, but the point is, something like this, out of bounds accesses are checked at runtime in Rust in general. Okay, so back to these common concepts. I'm going to use these. I'm going to use an example from Theseus, the system that I've written. It's a Safe Language OS. I'm going to use an example from the Page Allocator to illustrate each of these common concepts. Right now, the Page Allocator is the one that allocates a region of virtual addresses for you to then map to physical memory, and then you can use it. Right? So that's what a Page Allocator does. All right. So naming visibility. Typically in most languages, this relies on keywords like public, private, protected, whatever it may be. In Rust, as you know, it's pretty simple. You're either public or private. And if you're public, you can be public to a certain module path, right? But in general, let's just assume public or private, right? So if I have a function here called allocate pages, this is how I interact with the page allocator. I'll specify maybe I wish for these pages to start at this particular address, and I want this many pages, right? And I return either success or failure, right? Now this function is public, meaning that any other module can use it. It returns an instance of allocated pages, which is public, but this inner field that describes the actual range of pages that were allocated for you is private, so you can't modify it, right? And then within this public function, you can invoke private functions within the page allocator crate, right, within this module. And then these guys are the ones that actually do the allocation work to make sure that you don't have overlapping allocations or something like that, right? And I've omitted a lot of the details, right? But the point is, this is a private function, so you can't directly call it, right? So I can't mess with the page allocator's internal state, and it tracks pages in terms of free chunks, right? So I can't go over here and say, hey, please adjust this chunk for me arbitrarily, because this is not public, right? So this can only be called in the proper context, which is from within this function, right? Or within another function in this module, all right? So for example, you can't, and the only way to create an allocated pages, right, is with likewise a private internal function here from free chunk, right? So once the page allocator has determined that a given chunk is free, it can create and return an instance of allocated pages, which again is public, but you can't modify the internals, right? So that's what we mean when we say naming visibility. And I think through this example, you can see that just allowing someone to access the page allocator with this interface and this type, there's nothing that can go wrong. So that's kind of the point of naming visibility. Any questions there? I think probably that's the simplest one. Public, private, pretty straightforward. Okay. So then the next one is capability-like objects. And this is really just a fancy way to say that you have to be able to obtain a particular object to use it, right? Access its data or invoke functions that require that, right? So this allows you to effectively restrict who can have access to what types, what functionality, what data, just like hardware protection does with address spaces and privilege levels, right? So let's imagine, I have two different modules, two different applications per se, that want to allocate pages, right? So this first one runs, module one function runs, it allocates pages starting at hex 5000, and it allocates 10 pages. So that's hex 5000 through hex F1000, right? And this works because those pages are free. And then I have another module come along and say, hey, I'd like to allocate some pages that overlap that same region, 6000 through 7000, right? As long as everything works here, right, and I have these checks correctly, and I, basically as long as I've implemented my page allocator correctly, this will result in a failure, right? So what that means is basically once my page allocator has given module one the capability, right, the ability to access and own those pages and use them as it sees fit, right? It also needs to ensure that another module can't come along and access those same pages, right? So the capability is singular in this case. Only one module, only one entity can have the capability to access a specific page, right? And the way that I do that, again, this is in pseudocode, but there's a list of free pages, and I just check to see whether or not the address they requested is free, right? And there's more complexity, but that's the general idea, right? So the point is, pages here is an instance of allocated pages, and here pages is an error, right? And I'm omitting some error checking, but that's kind of the pseudocode here, right? So if you have an allocated pages object, right, as I showed previously here, that means that you have the ability, the capability to use those pages in a way that you see fit, right? So for example, one of the ways that you may use those allocated pages is to map it to some actual physical memory, right? And the way that you do that is you allocate some frames similarly, right? So for example, this is where your frame buffer also is. So perhaps you want to, display something on the screen. And then once I've successfully obtained an allocated pages and also an allocated frames, I can then go ahead and map memory, right? So basically, this is showing that in order to map a memory, you must have the capability, right? The ability to exclusively access virtual memory, exclusively access that physical memory, right? And then you also have to have some other things like the access to the page table, which is represented as another capability. But the point is, you need all of that stuff in order to actually map memory and then use it, right? And then we can do something like treat it as a 2D array of pixels because it's a frame buffer, right? So these are all examples of what I mean when I say capability-like objects are required or are kind of a fundamental building block for Safe Language OSes, right? Okay, so that's just a very basic example. Any questions on the first two? Okay, I have some more examples coming. So the third point, the third key concept was we have to be able to forbid unsafety, right? So all the things we just showed are great, they're fine and dandy, and they work awesomely, as long as nobody can circumvent those type safety and memory safety rules, right? So the best two examples of this are, like I said earlier, you can't arbitrarily reinterpret one type as another type, and you can't arbitrarily dereference random pointers, right? So let's say that I've allocated some pages here. I've allocated 10 pages at any address, and I've got them here, right? And in a system like C or something where you don't have the concept of like a public or private, naming visibility for a particular struct field, you could do something like this. You could just say, hey, I'd like to allocate myself 5 more pages, right? But I'm not going to tell the page allocator about it. I'm just going to do it, right? So I'm going to set the end of this range to, increment by 5, right? In Rust and in any system that provides type safety and through naming visibility, this would be a naming visibility error, right? And the only reason we can catch that is because of type safety, right? The compiler is checking that for us, right? Now, if we had an unsafe program or we allowed unsafe code, we could get around this, right? We could treat this reference to pages as a pointer, right? We could interpret it as a pointer of 2 tuples, which is kind of what a range is, right? You have a start page and an end page, right? And then with some unsafe code here, we could go ahead and dereference that pointer, access it as start and end, and then we could change the end value, which is effectively what we try to do here, right? Now this works, it's a legal code, but it requires unsafety, right? And it requires, specifically in Rust, it would require you to surround this random pointer dereference, right? Or any raw pointer dereference with an unsafe block. So you guys have probably seen code like this. So without unsafety, right, there's no way for you to get around, circumvent these type guarantees, right? So that's kind of the key point of having to, you need the ability to forbid unsafe. Here's yet another example, an even simpler one, right? Let's say that I know that my kernel is loaded at this address, right? FFFF8000 starts there, and I want to access the hex 1000th byte. So I can do something like this. I can access. I can treat this address as a pointer to let's say an array of 1000 bytes, right? And then I can just dump it, right? So this would work, right? As a pseudocode, but this would generally work in Rust. But of course, you need an unsafe block here because you're dereferencing this random pointer, right? So this is an example of arbitrary pointer dereferencing, and that's clearly not safe, right? It's clear that you shouldn't be able to do that. So if we can't forbid this, then we can't use this language, this ecosystem, to implement a safe language OS, right? So just to sum up, comparing Rust to C here, pretty obvious stark differences. Rust requires unsafe here. And I should also mention, in the Rust compiler, you can throw compiler errors if unsafe code is ever used. So for example, when I'm compiling applications for my system, I forbid unsafety to be used at all, right? So that guarantees that applications can't circumvent the rules that I expect and perform unintended behavior. In contrast, C obviously permits all of these operations, and it doesn't do any checks, right? Because it's not going to care whether or not you're accessing a particular thing, because it has no concept of safety. Right. So any questions on those three core concepts or the examples?
About the unsafety forbidden, being forbidden.
Sure.
I thought we learned earlier in the semester that like eventually we need to use unsafe code in order to do some things with the hardware. So how can we forbid all unsafe code? Like it seems like some is necessary.
Oh yeah. I wasn't saying that you will forbid all unsafe code. Is that you're able to forbid it where it shouldn't be used, right? So clearly in your core kernel, in a driver or something, you may need to directly access hardware or some register or something, and there's no way to avoid unsafe code there, right? The point is you would wrap that all up in a safe interface, and the application would only be able to invoke your safe function or use your safe types, right? That's the idea. So I mean, if you look at the Rust standard library, for example, there's boatloads of unsafe code, right? But the point is each one of those unsafe blocks has a very strict invariant, and you can only access it through going through other checks first, right? So, in the case of, copying a slice, for example, right? Copying one array to the other, right? Rust has all these guarantees that if you want to use the safe code version of that copying function, you have to meet all these guarantees that your type is copyable or clonable, that they have the same length, things like that, right? And then underneath the hood, once all those checks have passed, yes, there is some unsafe code.
Got it, thanks.
Yeah. Okay, so basically to sum up the idea of safe language OSs, right? There's a partition of trust and safety. And I think this is kind of what you were just getting at, Will, right? Unsafety is unavoidable in OS code, especially in some low-level contexts, right? Anything that directly talks to hardware, you're probably going to need some unsafe code, right? So the idea is to partition that. The trusted core is allowed to use unsafety, but it should be minimized. And then in untrusted or third-party code, like user applications or kernel extensions, unsafe code could be banned, right? So in that case, you as the system designer, maintainer, developer, whatever, you're able to say, okay, hey, I know that I wrote this unsafe code correctly, and no matter what anybody else does, as long as they only use safe code, all of my guarantees will be upheld. Right. So the final point then is that we derive the same kind of isolation protection that we derive from hardware using constraints imposed by the type system, right? So safe code can only access data, functionality, whatever, that are permitted by the types that it has access to, right? Okay, so there are quite a lot of existing safe language OSs. I'll just go over some of them real quick so you can get an idea that it's not super new. So back in the mid-1990s, I think the first major example of this is called Spin. It basically explored the ability to write kernel extensions, like loadable modules in Linux or drivers or something. And they ran in ring 0, but they had a very limited interface with the rest of the kernel. And they were written in a safe language called Modula 3. There's some other works like Inferno, but one of the primary works, I'd say the main example of a real safe language OS is Singularity from Microsoft Research. I definitely encourage you guys to go take a look at that. I'm not sure if Lynn discussed it in class, but it's a very robust exploration of different costs associated with hardware protection, like MMU translation and privilege levels, switching address modes. There are some other ones that use a little bit of hardware protection, but not all. For example, JX is a microkernel written in Java, right? But it's a single address space kernel. So it doesn't use hardware protection, but it does use, it does use hardware protection, but it doesn't use different virtual memory spaces, right? And then there are some more late works, like my own work on Theseus, and then an earlier work on Biscuit, or an earlier work on using Golang, right, called Biscuit from MIT. They basically said, if we just use the standard monolithic OS structure, but we use a managed language like Go, what's the overhead of that, right? And they found it to be, you know, a small percentage, 4 or 5% on average. Okay, so now that you kind of understand the idea behind safe language, so I have, what, 15 minutes? Okay, great. What are folks doing to push the boundaries of safe language OS, right? So in our group, we have this PIE conjecture, the PI conjecture. There are 3 pillars of computing goals: P for performance, I for isolation, and E for efficiency, right? And the idea here is that hardware can only provide 2 of the 3 effectively, right? Traditionally, system architects, like those who built monolithic OSs, they asked hardware to provide all 3 of these. And we would like to question that assumption. We think that hardware should only be responsible for providing performance, right? That is acceleration, speeding things up, right? And all other responsibilities should be left up to software, namely isolation and efficiency. And basically that translates to, let's explore safe language OSs. As you already saw, we can provide isolation in a more efficient manner. Right? So beyond that, you know, beyond taking over responsibilities of isolation, protection, efficiency from hardware, what else can safe languages do for us, right? Safety is nice. What else can we do? Resource management, right? So this is kind of the crux, I think, of most OSs, is managing resources and multiplexing them across the applications. So I'll use reference counting as a case study. So if you're not familiar with the concept of reference counting, it's basically a way to track how many users there are of a given resource, right? How many references there are to an underlying object or something, right? So it basically, it's a structure that includes a reference count itself, which is an unsigned integer, and some functions for acquiring and releasing that object, which basically just means incrementing and decrementing the ref count. And then the idea is that you can only free, you know, for example, deallocate that object when the reference count is 0, because that means nobody is using it, right? This is kind of how garbage collectors work, but they're a lot more complicated, right? So the idea is that developers are responsible for ensuring that the reference count is correct, right? And what that means is every time you increment the reference count, when you're done with it, you must also remember to decrement that reference count. Otherwise, you'll end up with some, you know, a leak, right? Or dangling references, right? So in this code example over here, we have, you know, this is Linux kernel-like pseudocode. All right, here we're incrementing a count for a particular device that we've acquired, right? Because we're using it, right? And then we're decrementing it. So we use it, everything, you know, goes well, and we decrement it. And then at that point, the reference count is right. It's 0 if we're the only user, and it can be free, right? However, what if we encountered an error when using that particular resource, that device, and then we jump here? We've skipped this reference decrement count, right? So at that point, we have a resource that is stuck. It can never be freed because the reference count is 1 higher than it should be. So it turns out, while this is a very simple example, it's actually a very prolific bug. There was a paper from the ASPLOS conference in 2016 called RID that discovered over 80 instances of these reference counting bugs in the Linux kernel. And they detected them using something similar to what I just showed, a form of static analysis to find inconsistent path pairs, right? Where you've incremented one case, but you haven't decremented it and all of the exit paths. All right. Their key observation was it's hard for both developers and the documenters, the creators of an API, to express and ensure that reference counts are incremented and decremented correctly in these pairs, right? So, you know, for example, if I'm the writer of this function and, you know, I'm providing the foo API to somebody else, am I responsible for guaranteeing that the reference count gets decremented when I return? Should I have the caller increment it before they call this function? Should I increment it for them, right? All of these things are hard to kind of capture in documentation and function prototypes, right? So surely we can do better than this, right? And yeah, we can. Rust does a lot better than that, right? So if you use Rust's built-in reference types, which are things like, of course, it's raw reference, it's the ampersand, or it's more intelligent runtime kind of reference types like arc or RC, it will handle all of this for you, right? So just don't use unsafe code and you're fine, right? So the idea is that you can have multiple people owning or referring to a given object, right? And the ref count is done internally and it's fully automatic. So basically when you acquire an instance, you clone an arc, for example, or an RC, it increments the reference count because you have one more alias to that object. And then when you drop it, right, it falls out of scope, it's destroyed, you decrement that reference count. There's literally no way for you to screw it up, right? So here's a simple example. I have this function that returns a device, but I'm wrapping it in an arc, right? So this means that not only is there, the underlying device, but there's also a reference count included in this structure, right? So then I'm creating the device. I've created one reference to it. So I have one ref here, a second ref here, a third ref here. I'm using it, I call this, right? At the end of this function, because I've passed it in by value, by ownership, right? Dev itself will be dropped. So I can use it and then drop it. So at this point, use device, device ref 1 has been dropped, right? And that means that the reference count within the arc will go back down to 2, right? Now I'm moving this device ref 2 into this thread, right? Into this closure here. And I'm calling do something on the device ref. So at the end of this scope, right, we'll see device ref 2 be dropped. So the reference count is back down to 1 just for this single device alias. And then at the end of the scope of the main function, this is dropped. The arc reaches a reference count of 0 internally, and the device itself can be released and freed. Right. And I'll show you how that works with some very simplified Rust code. So I basically looked at the inner implementation of Rust and dumbed it down significantly. And this is effectively how it works, right? You have an outer structure arc, which is just a non-null is basically a pointer, right? It's a raw pointer effectively. To an inner structure, which is literally just the ref count. For arc, it's atomic because it's thread safe. And then you have the underlying data, right? When you create a new one, you put it on the heap so you can have a pointer to it. You start the reference count at 1 to represent the current instance. And then you return it, basically from a raw pointer. You create this arc struct, and then you return it. Right. So then when you want to clone this reference, meaning that you're creating a shallow copy, right? You simply atomically increment the count. And then when a arc is dropped, meaning it falls out of scope, you simply you simply decrement the count, right? And if it's not 1, right, which means if you're not the only owner, then you don't drop the data. You only drop the data once you're down to 1, meaning you are the only owner, and then you can safely drop that data, right? So that's how it works. Okay, any questions on reference counting or how Rust makes it better?
I've got one, of course.
Yeah, go ahead. Yeah, sure.
Focusing in on the struct arc inner on the left, I don't think I ever fully understood what the angle brackets are doing. Could you tell me what the T is doing in that function? I mean, in that structure?
Yeah, it's a type parameter, right? So the easiest example is like vec, right? Vec is a list. So it has a list of one type, right? So the point is it's a generic type parameter. It's saying you can have any type, you can have an arc surrounding any type, an arc of any type, and that type is called T for the purposes of this implementation, right? So for example, if I wanted to accept a function, if I wanted to write a function that could accept any type, I could just have a function and I could parameterize it with T, and then I could say, arg1 is of type T, right? So you can read about generics and Rust. I think it's actually relatively simple, but yeah, the angle brackets here are just a generic type parameter, right?
So it's almost like how if you had like a pointer to like an integer in C, how you might cast it to a void pointer so that you could use it as other kinds. It's kind of like that.
Yeah. In concept, yeah, conceptually, it's very similar to that. In the implementation, it's not, right? Because you still have the guarantees of like, the size of this type, the alignment, all those type safe properties. But yes, that's the same principle. Yeah.
Cool, thanks.
Mm-hmm. Yeah. Okay. All right, so in the last couple of minutes, All right, yeah, I got to wrap up soon. So we can use language to go beyond just safety. We can have, better reference counting, right, to avoid ref count bugs. Can we go even further, right, to ensure that resource management is always correct? So that's kind of the one of the leading design ideas behind my system, Theseus. And I'm just going to give you a very brief example of what you can do with this. Right? So in a nutshell, Theseus is a safe language, single address space, single privilege level system written in Rust, right? So the goal of the system, one of the goals, is to maximally empower and also maximally leverage the language of the compiler, right? So we can push the boundaries of type and memory safety. So blah, blah, blah. This all sounds like a bunch of marketing jumbo. But the point is that what I want to do is offload as much of the resource management responsibilities from the OS at runtime into the compiler, right? And I call this interlinqual design. The idea being that you're designing the OS within the bounds of the language, right? As opposed to doing things beneath the language level such that the compiler can't check it and it can't see it. So the idea is to unify, like I just said, unify the view that the OS has and the understanding, the semantic understanding that the OS has of the system and its resources with that of the compiler and its view and understanding of language abstractions, right? So the reason here is the Rust compiler can already check a bunch of built-in safety invariants, right? Using its type and memory safety guarantees about the semantics usage of threads, stacks, and the heap, right? We're all familiar with this ownership concept, right? Moving things across threads. Is it safe to move across a thread? Does it live long enough on a given stack frame, right? When can you deallocate from the heap? All of these things, right? Rust has built in. The problem is that only applies to memory on the stack, memory on the heap, and a very basic thread model, which is only in the standard library, right? In an OS, you don't have all of these things. You have stacks in the heap, right? But you may have different thread model and you have arbitrary memory regions, right? So there's a whole bunch of other resources that the compiler cannot and does not know about, but the OS does. So the point is to basically connect those two, right? And the goal then would be to ensure safe resource management. And what that means is acquiring a resource, accessing that resource, and then releasing it at the right time and having the compiler help us determine when it's safe to do so, right? So you can consider this being applicable to anything from memory to reference counts, allocations, locks, right? Anything that's sort of reversible, right? Has an acquire release pattern. And like I already said, this is facilitated by Rust ownership model and its borrow checker, right? So the idea is that there's a one-to-one relationship between a hardware resource and a software object that represents that resource, and then it can be freed after the final owner, the exclusive owner, is done with it. Its scope ends, the software object falls out of scope, and we can free the resource at the hardware level, the OS level. All right. So to do so, there are a couple things we had to do to design the OS in a slightly different way. To allow the compiler to view the whole system, we have to match its expected execution model, right? All compilers have a model of the world. To allow it to understand things, we have to implement all OS functionality using that strong static type system and all of the existing abstractions that the language already provides. All right. So I'll just go into real brief detail here. To match the compiler's execution model, we basically have to have what I call a bijective address space, which is just a fancy way of saying a one-to-one mapping from all virtual addresses to all physical addresses, right? And there's only one single address space, so there's one single set of visible virtual addresses across the whole system, right? And this is what the compiler expects. If you think about a compiler, it expects that you're going to basically take this code and build it and run it as a program, maybe a multi-threaded program, but it's all within one single process, which means it's within one single address space, right? So we're kind of forced, if we want to allow the compiler to see the whole system, we're forced to use a single address space across the whole OS. All right. Already talked about single privilege level. There's nothing super neat about that other than the compiler doesn't know about privilege levels, right? You can't build a system that the compiler can say, hey, this runs in ring 3, this runs in ring 0. Compiler doesn't know about that. It doesn't care. There's some other details. The compiler only has one allocator instance, although that's changing in Rust. So we may revisit this. But these are the ideas to make the compiler be able to view all of the system entities, right, across the whole system. And then to actually implement things, right, of course, we have to use safe code as much as possible. And then we have to identify all the invariants to prevent unsafe, or more correctly, more precisely, incorrect usage of resources, right? So for example, instead of using something like raw pointers, like you see all over the Linux kernel, we'll use references with lifetimes, or these reference kind of types like arc and RC for safe aliasing. That way the compiler can check to make sure all of the aliases across the system are, they still last, or they're lasting as long as they need to, or there are no more aliases before we free a resource, right? And then we also do a lot of fancy stuff with new type patterns and session types, which I don't have time to get into, but basically clever usage of the type system to make it impossible for the programmer to represent invalid states for a resource to enter. Right? All right, so one quick example, let me see, okay, yeah, 3 minutes. One super quick example is a type called mapped pages, which I briefly introduced earlier. That's basically a memory region that is guaranteed to be mapped and legally accessible for as long as you hold on to that map pages object, right? So this guarantees, for example, to the language in a way that the language can check it for us, that there is a one-to-one virtual to physical mapping, meaning you can't have any aliasing beyond the language. You can't access that memory region beyond its bounds, right? So no buffer overflow. You can't mutate or execute that memory region, right? You can't treat it as writable or executable code unless it's mapped properly, right? So this is something to do with page tables. And then you also make sure that it gets unmapped exactly once, only after everyone's done using it, and then it can't be accessed. It can't be accessed after being unmapped, right? So that's avoiding dangling pointers. So the idea that behind map pages is we're empowering the compiler to basically guarantee that for all memory regions, including ones that it doesn't know about ahead of time, like the stack and the heap, that there's no way you can invalidly use it, and you're not going to have any weird seg faults or anything as a result of using that memory. Right? So this is an example of going way beyond just basic safety, and allowing the compiler to do some level of resource management for us. Right. Another thing we do is prevent resource leakage. I do that through unwinding, but I don't really have time to get into this. Right, so there are a lot of benefits. It reduces the states that the OS has to maintain. So the OS is overall simpler because the compiler is maintaining a lot of these states statically at compile time. So it knows when it's proper to free a resource or something, right? Also down here in blue, a key part is that it removes this notion of a semantic gap in the compiler's understanding of code. And this is, if you're familiar with compilers, this is kind of a known issue, right? The compiler only knows about what it knows about. And that's obviously a tautology, but the point is it can't know about parts of the hardware that it doesn't have a model for, right? So the point is of this interlingual design approach is to expand the compiler's knowledge, right? And with that, we can approach end-to-end safety, right? You have a purely safe interface from the top level application all the way to just almost at the very lowest level of the kernel, right? And then we hit hardware where, like I said before, we have to use unsafe, right? And you also get a lot of runtime errors being shipped in a compile time, so you can catch them earlier. It's a lot easier for developers. As you probably know, it's quite difficult to debug an OS, so hitting random runtime errors isn't great, and it's not user-friendly. Yeah. Right, so yeah, let me just wrap up real quick. So that's the idea behind safe language operating systems. They forego hardware protection by using things like type safety, memory safety, naming visibility, forbidding unsafe, all these different features, right? And I think the thesis point here is that hardware protection is good, it's inefficient, right? Safe language protection can be more efficient due to less overhead transitioning between these modes, but it's also could be weaker, right? I don't want to paint safe language OSes as like a panacea for every single environment, right? One, you have to use a safe language to write everything, which is maybe an undue restriction, especially if you have large amounts of legacy code, right? But more importantly, it's, if you mess up your safe to unsafe interface, then you hit the same problem of a potential security hole as you do in hardware if you mess up configuring one of those system descriptor tables, right? So it's not invincible. But one major point is that it's a lot easier to verify because it's just regular source code. All right. And then finally, more recent safe languages have gone beyond safety and gone beyond isolation, like my own work to ensure proper resource management in the compiler. And I think that's just about it. Yeah, that's all I've got. So I hope you learned something about Safe Language OSes, and I'll stick around to answer any questions that you may have. Okay. Thoughts, comments?
Why the name Theseus?
That's a good question. Are you familiar with the paradox of Theseus's ship?
Yep.
Yeah. So for those of you not familiar, the idea is it's a thought paradox. If you have a wooden ship and you've built it out of all of these wooden planks, if over time you replace every plank with a new one, at the end you've replaced every single wooden plank, so there's no original pieces remaining. Is it still the same ship? Right. I like that thought paradox. That's where the name came from. Because another goal that I mentioned of the OS is to be able to replace any arbitrary component at runtime. I didn't discuss that today because it's not relevant to language safety, but yeah.
I was going to guess something like if you replace every part of Linux with a safe version of Linux, like, is it still Linux?
Yeah, so there's actually a lot of interesting, I don't want to derail the conversation too much, but there's a lot of interesting developments in the Linux world, right? They're looking at finally allowing a second language into the kernel, which is Rust, right? So you might have heard of this. And they're looking at it just for very light usage for additional drivers, new drivers that are being added to the kernel. It would be a monumental effort to rewrite parts of the kernel in Rust. And, like many kernels, especially in Linux, it would be a crazy amount of unsafe code. So if you have a system where there's so much unsafety required, is writing it in Rust really a benefit? Yes, but it's a lot of work, so the benefit is minimal. All right. If that's it, yeah, I'll share the slides on Slack, and yeah, I guess we've come to the end of the class time. So yeah, I hope you enjoyed the whole course. Hope you enjoyed the assignments. We tried not to make them too hard, but obviously anything systems related is difficult. So forgive me for that. Yeah, have a good summer, and we'll see you guys later.
Thank you.
Thank you.
No
Yeah,
problem.
thanks.
All right.
Thank you.
Bye-bye, guys.